In this video, we're going to do chapter 11. So let's start with section 11.1, which is review and preview. So we're going to review a couple of things that we have touched on briefly in the past and then look forward to the rest of the chapter. All right, so the chi-squared distribution. So let me try to get to the pencil and not the highlighter. So in a chi-squared distribution, here's how it is set up. In a normally distributed population with variance sigma squared, assume that we randomly select independent samples of size n, and for each sample compute the variance s squared. So remember, this is the population variance and this is the sample variance. The sample statistic of chi-squared has a sampling distribution called the chi-squared distribution. So you have seen this formula in a previous section, but I'm going to reiterate it here. Chi-squared is equal to n minus 1 s squared over sigma squared, where the degrees of freedom, or just df again for short, are equal to n minus 1. So the same degrees of freedom as the t distribution. So here are three properties of this chi-squared distribution. Chi-squared distribution is not symmetric. So this isn't like the normal distribution or the t distribution in that respect because it's not symmetric. So you can see at the bottom of the page here, I'm not going to scroll down because it will be a little bit confusing, but there is an example of a chi-square distribution that is skewed to the right, and so it's not symmetric, but it is a little bit skewed to the right. All right, so that means it has a longer right tail. 2, the values of chi-squared can be 0 or positive, but not negative. So you can also see at the bottom of the page that the distribution that is given starts at 0 and goes up. So this is not a distribution that goes from negative E99 to E99 or from negative infinity to infinity. All right, so property 3. I'm going to try to fit it in here so I don't have to scroll the page down on you. So the chi-squared distribution is actually different for each number of degrees of freedom, but as the degrees of freedom increase, the chi-squared distribution approaches a normal distribution. So again, it will never be symmetric, but it will approach a normal distribution. So approaches a normal distribution. So the one that is given down at the bottom of the page, you can see is for a degrees of freedom of 9. So we're going to use a calculator to verify the critical values that are at the bottom of the page here. And I typically won't have you do the critical values for the chi-squared distribution by hand a lot. And so the one thing that I want you to note is that on Canvas, I put a chi-squared calculator online. So if you don't have the program that I'm about to show on the calculator, then you can always use the online program, and I won't take offense to that because I won't actually have you ever calculate this by hand uh, at, at, at a test. You can just do this at home on the computer. All right, so here we go. Let me pull up the calculator so that we can go ahead and verify these values here. So I'm going to start by verifying this lower critical value. And so I'm going to use the program. So the program is going to be here. So program, and then I have the IMV chi-squared program. And then it says the area to the right. So I see the area to the left of this value is 0.025. So if I have IMV chi-squared, the area to the right is actually 1 minus the 0.0025. So I'm going to type that in, 1 minus 0.025. And then did I put the decimal place in the wrong spot? Sorry about that. The degrees of freedom are 9. So they told me that in this case. So it might not be 9 every time, but the degrees of freedom are 9. And then I can see right here it's thinking, and I get the 2.700. So if you didn't like that, you could go to the critical value calculator that I have here, and if I type in the degrees of freedom are 9 and then 1 minus 0.025, I think I can do it that way. Then I can calculate that. Oh, you know what? This calculator makes you do the 0.975, so you actually have to subtract that. And you can see that I get the same value of 2.7003895. So that's perfectly fine to do that. So now I'm going to come over here and I'm going to verify the right critical value. So the one on the right, I'm going to verify the 19.023 now. So program and inverse chi-squared. And the area to the right is going to be 0.025. So let's go to that. Program inverse chi-squared. Oops, it's off screen. Enter 0.025. Degrees of freedom are still 9. And then I can see right here that I get the 19.023. And again, if I wanted to do that using the computer, I could type in 0.025 as the area to the right and hit calculate here, and it will give me the 19.02276,780. So I think that's pretty cool. At least I do. So now I also want to show you how to verify that this middle area would actually be 0.95. So I can do that by using the X2 area program. And I'm not going to show you that on the computer because I think that is something that I'm just doing to show you that this area is just 0.95, no other reason. So program and then X2 area, enter, in the degrees of freedom, enter 9, enter, then go to the left value, and the left value was the 2.700, so 2.700, and then I go down to right point, enter, and that was the 19.023, enter, and then go down to find area, and I see that the area in the middle between these two values of 2.7 and 19.023 was actually 95. And then enter, and then I can go down to quit and quit out of there and be all cleared out to go on to the next example. All right, so that is a quick overview and preview of the chi-square distribution. And now I'm going to move us on to the next section. So the goodness of fit test. So a goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. So I'm going to go ahead and write down what these hypotheses are. So H0 is that the observed frequency, and I'm going to call them O, is equal to the claimed distribution, or what you are expected to get. So O is equal to E, or in other words, in no jargon, the distribution is a good fit. And that is why this is called a goodness of fit test. Versus H1 or HA, right, either is okay. The observed frequencies are not equal to the expected frequencies, or in other words, the distribution is not a good fit. So there are three requirements here. The data have been randomly selected. The sample data consists of frequency counts for each of the different categories, meaning that none of the categories have a zero count. And the expected frequency should be at least 5. Now, the observed frequency doesn't need to be 5, but the expected frequency should be at least 5. If it's not, there's possible problems, but you should try to make sure it's at least 5. Now, the next little part here just gives some of the notation. So let me go through some of the notation, and then we'll get through a couple of examples of actually calculating some things. So again, to review, O is the observed frequencies. Oh no, I think I spelt that incorrectly. Let's see. Is it CIES? There we go. And E is for the expected frequencies. What a time to be alive, right? K is the number of different categories. Excuse me. And then we have N is equal to the total number of trials. So there's two ways or two cases of when you might need to calculate E. So case 1 is when all of the expected frequencies are equal. And if this is the case, E is equal to N, the number of trials equal to the number of different categories, meaning that the probability of each category is exactly the same. In case 2 is when all expected frequencies are not equal. So when they are not equal, then E will be your normal N times P formula. Right, so this is actually N times P, where P is just 1 over K, but it's just a shortcut way of saying it. And then the test statistic is chi-squared is the sum of the observed minus the expected frequency squared divided by the expected frequency squared. Sorry about that. I don't know what all of these messages are doing coming up here. All right. So that is the end of this page. So let me tell you about the critical values and the p-values. and then we'll do a couple of examples. So the critical values, these are one, either found using the INV chi-squared program, or a computer, or if you really want to be old school, and I know some of you are, table A4 with, now please note this, it's K minus 1 degrees of freedom. All right, so this is the number of categories minus 1, not the number of trials minus 1. And then the second note is that the GOF, or the goodness of fit test, are always right tail. And that is why when we started this chapter, I was always making sure to find the area to the right and not to the left. All right, so the p-values, we're going to actually find the exact p-values, but I want to remind you of a couple of things. A close agreement between the observed and the expected value, meaning that the distribution is a good fit. All right, so the distribution is a good fit, means that you are going to have a small chi-squared and a large p-value, meaning that, in other words, you are going to fail to reject H0 because the p-value is high. So that's 1 here. And then 2 is when you have a large disagreement between the observed and the expected frequencies. And again, that would mean that the distribution is not a good fit. And that means that you are going to have a large chi-squared and a small p-value, which means that in this situation, if the model or the distribution is not a good fit, you are going to reject H0, meaning that you're rejecting that as a good fit, and it's actually not a good fit. All right, so the next page is going to be our first example of this exciting topic in our life. So let's go to this. No, you can read this next chart on your own. I don't want to read that to you. This is a very long example, so I will let you read it on your own, but I want to bring you to the key parts of this so that you know what they are. So this part right here says if people are actually weighed with a scale having precision to the nearest 0.1 pound, the weights tend to have the last digits that are uniformly distributed, with 0, 1, 2, 3 through 9 all occurring with roughly the same frequencies. So this is the key. And I know that we talked about this, that if people are estimating their weight, it's more likely to end in 0 or 5 because they're rounding their weight. And if they're actually measuring their weights, the digits will be more uniformly distributed. So let's go to the example here. Test the claim that the sample is from a population of weights in which the last digit do not occur with the same frequency? And then based on the results, what can we conclude about the procedure used to obtain the weights? So let's write down the null and alternative hypothesis. So we are testing the claim that the digits do not occur with the same frequency. So H0 is O is equal to E, meaning that the last digits do occur. Why is there another messages here? All right, the last digits occur with, oh no, now it changed colors, with the same frequency. And H1 is O not equal to E, meaning that the last digits do not occur with the same frequency. All right, so this was the claim, that they do not occur with the same frequency. So we need to remember that for page 195. Now, these are going to be the observed frequencies that they gave you, the O's. And then there are 10 categories. So K is equal, okay, then why? K is equal to 10 categories. All right, it really wants this to be a thicker marker there. What a time to be alive, right? All right, let's try one more time. Sorry about that. So K is equal to 10 categories. There we go. 0 to 9. Now, I'm going to make a separate column for the expected categories here. And remember that if these are all equal, then the formula is N over K. So the total number observed is equal to 80 here. So you can add those up and see that you are actually going to get 80 here. So then 80 over 10 is actually 8. So all of these are going to be 8. So you're expecting there to be 8 in every category if these are all equal. But if you look at what's going on in some of these categories, it's a little bit higher than 8, and in some of the categories, it's a little bit lower than 8. I think you know what, turning the pen for whatever reason. So hopefully I have turned a new leaf. Now, what I want you to do for the steps for this is to use the calculator. So here are going to be the steps. So try to follow along with the steps. All right, so I'm going to actually erase K equals 10 categories so that you can see all of the steps fairly clearly. And the steps are going to be that you're going to enter the data in L1 and L2. So stat, edit, and if you have something in there, clear it out. So I'm going to enter the observed and the expected frequencies, not the last digit 0 through 9, but just the frequencies. So 7, enter, 14, enter, 6, enter, 10, enter, 8, enter, 4, enter, 5, enter, 6, enter, 12, enter, 8, enter, and then go over and enter 8, 8, 8, 8, 8, 8, 8, 8, 8, 8. Okay, so now that I have that, and if I went too fast, feel free to pause this. I don't really care. I won't be offended. All right, so second, and then quit. Then we're going to go to vars, oh, no, here is stats, sorry about that, stats, and then test, and here is chi-squared GOF test. So remember, we're doing a goodness of fit test, so we want chi-squared GOF test. So you need to enter the data in L1 and L2, and then use this chi-squared GOF test. So hit enter, and then it should say the observed and the expected are in L1 and L2. So the observed, again, was L1, the expected was in L2, and the degrees of freedom are k minus 1. So it's going to be 10 minus 1, or 9. So I'm going to enter 9 here, and then go down to calculate, and I see that the chi-squared test statistic is 11.25, and the p-value is 0.25896125558. So that is a high p-value, p-value high, so you're going to fail to reject 80. So that means that therefore there is evidence that the digits appear to occur with the same frequency. So there's evidence that the digits appear with the same frequency. Now, I'm not actually sure that that is the exact same wording as page 195. The, the sentences say the same thing. Right? So what we're saying is that we have evidence for that. We do not have evidence to support our claim. All right, so that is the end of page 247. So now I'm going to move on to page 248 and do another example of this. Now, by the way, if you ever need to calculate that 11.250 by hand, here is all the work that you would have to do to calculate the 11.250 by hand. So let's do another example of calculating this. So the study was made of 147 accidents that require medical attention. And among those accidents, so let me write that out, by the way. N is equal to 147 accidents. Excuse me. And 31 occurred on Monday. So I'm going to make a little table. Monday, number of observed accidents. So 31. And then Tuesday was 42. Wednesday was 18. Thursday was 25. And Friday was 31. Then use a 0.05 alpha 0.05 significance level to test the claim that accidents occur with equal proportions on the 5 workdays. So O is equal to E, meaning the accidents occur with equal proportions, and otherwise H1O is not equal to E, meaning that the accidents don't occur with equal proportions. All right, so now I need to find the expected number of accidents each day. And because I'm talking about equal proportions, then E is still equal to N over K. And there are K is equal to 5 categories because there are 5 days of the week that, oh, I didn't include Monday, that are located here. All right, so I'll try to make that look a little bit nicer for you. There we go. So there was 147 over 5 days. That's 29.4 accidents expected each day. So then I need to put that information in L1 and in L2. So what I'm going to do is bring up the calculator again so that you can see that the information is being put into L1 and L2. So let's see, stat, edit, and then make sure that you clear out the information from the previous problem. So clear out all of those 8s that we had. All right, so we have 31, enter, 42, enter, 18, enter, 25, enter, 31, enter. Then we have 29.4, 29.4, 29.4, 29.4, 29.4. Now we're going to go and quit out of there. So hopefully you had enough time to enter all of those. Then go to stat, then test, and chi-squared GOF test, and hit enter. And remember, the degrees of freedom are, here, that might actually be better if I put it right about there. The degrees of freedom are k minus 1, and k was actually 5, so this will be 4. So let me write all of that down for you. We're going to use the chi-squared GOF test, and the observed is going to be L1, and the expected is going to be L2, and the degrees of freedom k minus 1 or 5 minus 1 is 4. And then I'm going to calculate that. So I'm going to go down and hit calculate here, and then write down the test statistic or the chi-squared value of 10.65306122 and the p-value of 0.030752653. And then I just have to think to myself, is that p-value high or low? Well, that p-value is less than the alpha of 0.05, so the p-value is low, so I'm going to reject HO, and that means that there's evidence that the accidents do not occur with equal proportions. And by the way, yeah, all I'm saying is that if I'm rejecting H0, that I'm actually have support for this, that the accidents don't occur with equal proportions. So if this were the claim, then in this case, I'm saying that there's evidence to support the claim that accidents don't occur with equal proportions on the 5 work days. So that means that, yeah, Wednesday had maybe an unusually low number of accidents, and maybe Tuesday had a very high number of accidents. but that could mean that the people who were accident prone all had their accident on Tuesday and then stayed home on Wednesday. Who knows what actually happened there? All right, so what a time to be alive. Now let's do one more example, and this one will be of Benford's law. So this law is an example of one where the proportions are not going to be equal. So let's go and try that one right now. So here it is. And this one might seem like it's going to be a lot more work, and you're right, it will be. So I'll try to leave enough room for us to have room for the whole problem here. All right, so but you can see here that pretty much that they're trying to figure out if you can detect fraud by just looking at the numbers on the checks. So the number of checks that were issued was 784. So there were 784 checks issued total, and they had frequencies as follows. So I'm going to write down the observed frequencies under each of these. So 0, 15, 0, 76, 479, 183, 8, 23, and 0. All right, so maybe you can't read the 23 there. I'll try to make it a little bit more legible, but it's the same number that's already on your paper right here. Now, if the observed frequencies are substantially different from the frequencies expected with Benford's law, then the checked amounts appear to result from fraud. Use the alpha is 0.01 significance level to test for goodness of fit with Benford's law. Does it appear that the checks are the result of fraud? So H0 is that O is equal to E, or the frequencies are the same. And if they're the same, that means that there's no fraud. And H1, the observed, is not equal to the expected frequencies, meaning that the frequencies are different, and that means that there is fraud. So now, just be aware that I'm going to use the same chi-squared GOF test here. So now, let's go back to the calculator. And I want to enter the observed and the expected frequencies in the calculator today. Now, because these are not equal, I know they're not equal because they're giving me the percentages that these are all happening at, then the expected values or the expected frequencies are not n over k. It's actually going to be n times p. All right, so that's when the frequencies are not equal. And I know they're not equal because they're telling me different percentages or frequencies for each category. Although there are 9 categories, I'm not going to say that each of the digits is occurring equally here. All right, so now what I'm going to do is I'm going to go to Stat and then Edit and clear out of the L1 and L2 so that I can type in my new observed and expected frequencies. So they were 0, then 15, then 0, then 76, then 479. Oh no. Okay. I am just going to use the keyboard from now on. So 479. Okay, that didn't work either. 479. Okay, what a time to be alive. So let me get back to the screen. All right, 479, then 183, and then 8, and then 23, and then 0. Now, the expected frequencies, I'm not going to calculate by hand, but I'm going to see that they're all n times p. So m was 784, and then p was 30.1%. So 0.031. So times 0.03, 301, 30.1%. And then the next one is 784 times 0.176. And the next one is 784. See, I'm not sure why my delete is not working here. Okay, 784 times 0.125. Okay, I clicked multiplication and it put I in there. What a time to be alive. All right, 784 times 0.125. There we go. Then the next one is 784 times 0.097. And the next one, 784 times 0.079. And the next one, 784 times 0.067. And the next one, 784 times 0.058. And the next one, 784 times 0.051. And the next one, 784 times 0.046. Now I'm going to quit out of there. Hopefully you have them all typed in right. I hope that I do after all of that struggle. I'm going to go to stat and then test, and then the chi-squared goodness of fit test, and then the observed is L1, and the expected is L2, and then the degrees of freedom are always k minus 1, so observed L1, expected L2, the degrees of freedom k minus 1, or k was 9 categories, so 9 minus 1, 8. So 8. Okay, then. My 8 isn't even working now. 8. And then I'm going to calculate this and write down the chi-squared value and the p-value just like before. So that 3650.251371, and the p-value is 0. So of course that is low. P-value low, you're going to reject HO. So that means that there is fraud because the frequencies are different. So if you want to answer the question, does it appear that the checks are a result of fraud? Yes. There is evidence that the checks are a result of fraud. So if you want to know how to be spotted, writing fraudulent checks, just make sure that they have these observed frequencies, and you will be spotted for fraud. It works every time. What a time to be alive. All right, now it is time for the final section in this chapter. So let's move on to section 11.3, contingencies tables. So a contingency table is sometimes also called a two-way table, and is a table in which the frequencies can correspond to two variables, and one variable is used to categorize rows and the other to categorize columns, and there are at least two rows and two columns. Simple enough. In the test of independence, test the null hypothesis that in a contingency table, one of these two-way tables, the row and column variables are independent. So in other words, H0 is that the variables are independent, and H1 is that the variables are dependent. And please note that this procedure cannot be used to establish a cause and effect relationship between the variables in, oh boy, that's supposed to say in question, not in equation. All right, so the variables in question. So again, correlation never implies causality. So that's all that sentence is here to say. So there's three requirements. The sample data are randomly selected. They're represented as counts in a two-way table. That's why we're talking about two-way tables. And for every cell in a contingency table, the expected frequency is at least 5. So that is exactly the same condition as in the goodness of fit test, that the expected frequencies all still need to be at least 5. All right, so let's try to go on to the notation here, and then we'll do 3 quick examples, and then we'll be done. So here is the notation here. So the notation is that E is equal to the row total times the column total all over the grand total. And I'm not going to make you calculate E by hand. So if you don't know what row total is or column total is, that's fine. We'll use the calculator to calculate that. The test statistic is still the same. And again, the calculator will tell you this, so we're not going to calculate it by hand. And the critical values, you're going to use the degrees of freedom in this case, not k minus 1 like the last section, not n minus 1, but they're going to be r minus 1 times c minus 1, where r is the number of rows in your two-way table or your contingency table, and c is the number of columns in your contingency table. And then please make a note that test of independence are always right tail. Just like for the goodness of test, these are also always right tail. So again, you might want to calculate the degrees of freedom by hand once in a while if you want to make sure that your calculator is giving you the right value, but you really don't need to calculate these by hand. All right, let's go to the next section of examples here. So I'm going to make this a little bit larger for you to see again. Oh no, the struggle is definitely real. I don't know how this oh no, now it's upside down. Just turn your computer upside down, it will be fine. Now, here is an exciting example about wearing seatbelts and the number of cigarettes smoked per day. Now, of course, these are not going to be related in a cause and effect relationship, but we can still see if these are independent of each other or not. So, seatbelt use independent of cigarette smoking. So, I'm going to let you read this on your own, but we're going to test the claim that the amount of smoking is independent of seatbelt use. My highlighting is not very good on this. I apologize. I never liked highlighting ever in my life. Highlighters are too expensive. They need to lower the price of them. I hope that you would agree with that. All right. Let's go ahead now and write down the null and alternative hypothesis. So remember, H0 is always going to be that the variables are independent. So smoking and seatbelt use are independent. And H1 is that smoking and seatbelt use are are dependent or not independent. All right, so not independent. So our claim is that they are independent. Now this is a two-way table, so the number of rows is equal to 2, and the number of columns is equal to 4. So the degrees of freedom is r minus 1 times c minus 1. So 2 minus 1 times 4 minus 1, which is 1 times 3, which is 3. So if you want to calculate that by hand, you could. But when you have a two-way table, the first thing that you need to do is enter the data in the calculator. So we're going to enter it a little bit differently than before, because instead of just having one variable, we have two. So pay attention to this, and we're going to go to second and then matrix. Now it doesn't matter if there are other things already in here. You're just going to go over to edit and hit enter, and then enter 2, enter 4, enter for 2 rows and 4 columns. And then you're going to type in all of the numbers. 175, enter, 20, enter, 42, enter, 6, enter, 149, enter, 17, enter, 41, enter, 9, enter. So make sure that you have a 2 by 4 table or a 2 by 4 matrix in your calculator, and all of the numbers are entered here. Now press second and then quit. Now, even if you didn't have the GOF test in your calculator, you should have this next one in your calculator, and that's going to be the chi-squared test. So we use the chi-squared test for a test of independence or homogeneity, which I will get to in the next example or two. So go to stat and then test and chi-squared test. Now make sure the observed is in A and the expected is in B. Now remember, we didn't actually put anything in B, but the calculator will calculate all of the expected values for us, or the expected frequency for us. So we don't have to do that. So we go down to enter, and here we go. We have the chi-squared value is 1.358175464, and the p-value is 0.7153672,396. So I'm going to minimize. Oh, by the way, if you ever need the expected frequencies, you can go into second matrix, and then go down to B and hit enter and enter again, and these will be all of the expected counts or the expected frequencies. All right, so now this is actually a high p-value because it's higher than 0.05, so the p-value is high, which means that we fail to reject H0. That means there's evidence to support our claim that smoking and seatbelt use are independent. So there's evidence that smoking and seatbelt use are independent. Wow, I wouldn't have guessed that they're independent. I mean, my dad is a smoker and he doesn't wear a seatbelt. So I wouldn't have ever guessed that they were independent because I would have just thought, based on my dad and seeing him being a smoker who doesn't wear his seatbelt, that all smokers are like that. But apparently, that is not correct. All right, now what a time to be alive. It is time for the next example here. During the recent economic recession, many families faced hard times financially. Oh no, not again. Rotate clockwise. It's upside down, upside down. All right, here we go. So, some studies observed. Now, by the way, if this doesn't rotate and stay that way, I'm going to sue for damages here. Many families face hard times financially. So some studies observed that more people stop buying name brand products and start buying less expensive store brand products instead. Data produced by a recent sample of N equals 700 adults and whether they usually buy store brand or name brand products are recorded in the following table. So using a 1% or alpha is 0.01 significance level, can you reject the null hypothesis, H0, that the two attributes, gender and buying name brand, are independent? And then that would mean that H1 is that gender and buying, there we go, buying name brand, I think I spelled independent. Okay, there we go. Sorry about that. I am not that good at spelling, but I will try. That's all I can guarantee here. So gender and buying name brand are dependent. All right, so I'm going to enter this table in the matrix. So let's go ahead and do that today. All right, so now for some reason the calculator has disappeared. So I'm going to enter here and bring up the calculator again. For whatever reason it disappeared on us. So here's the calculator. And that's the timer. All right, so let's go to second in matrix and go over to edit. And this one is 2 rows by 2 columns. So I'll make sure it's 2 by 2. and enter the 150, the 165, and the 160, and then the 225, and then second, and then quit. So now we're going to go to stat, and then test, and then chi-squared test. If I can get this thing to cooperate here. All right, chi-squared test. And so, again, this is actually easier than the test of independence because you didn't have to calculate the expected counts or frequencies on your own. So the observed is in A, the expected is in B, and then we're going to scroll down and calculate this and then write down our test statistic, our p-value, and our conclusion. So x or chi-squared is 2.5791429, and the p-value is 0.108203.874. So I'm going to close that, and that actually is a high p-value because it's higher than 0.01. So the p-value is high, so then you're going to fail to reject H0 because the null will fly. So if your claim is that they're independent, then again, there is evidence to support the claim that gender and buying name brand are independent. There you go. So that is the end of page 251. Hopefully seeing another example of using the chi-squared test was helpful. So let's do the test of homogeneity, and then we'll be done. So, homogeneity. In these tests, we test the claim that different populations have the same proportions of some characteristics. So, for these tests, H0 is going to be that they have the same characteristics, or H1 is that they do not have the same characteristics. So I'm going to do this example here. And remember that in this chapter we had the goodness of fit test and the test for independence, and now we have the test for homogeneity. Here it is. In the judicial case of United States versus City of Chicago, fair employment practices were challenged. And so a minority group, Group A, so I'm going to mark Group A as the minority, and a majority group, Group B, took the fire captain examination. Assume that the study began with predetermined sample sizes of 24 minority candidates. So you can see here that the total number of minority candidates was 24, and then the total number of majority candidates was 562. So that is how you determine between a test of homogeneity and a test for independence. Homogeneity tests have predetermined sample sizes for different populations, like this example does. And the test for independence just uses one big sample which is drawn so that the column totals are determined randomly. All right, so that column totals are determined randomly rather than being predetermined like 24 and the 562 were. So H0 is going to be that the proportions are the same. The proportions of minority and the majority candidates who are passing this test is the same, meaning that the test does not discriminate. And H1 is going to be that the proportions are different. So the proportions are different. I don't know why that happened. Oh no, it's gonna be that different color now. Oh no. Alright, so the proportions are different, meaning that the test does discriminate. Now, you are still going to use chi-squared test, and you're still going to put the table in A, and then the calculator will calculate the expected values for you. But I want you to try this one on your own, and then check that these are the values that you get, just so that you definitely have tried one on your own. All right, so pause the video or do whatever you have to do. Make sure that you take a moment to enter the observed matrix into A, and then go to chi-squared test and get this test statistic and this p-value. All right, now they want an alpha is 0.05, so this p-value is actually low because it's less than 0.05, so we're going to reject HO, which means that if we're rejecting HO, or the null hypothesis, that means there is evidence that test does discriminate. So there is evidence that the test does discriminate. And I could have told you that sort of by doing a visual test and saying that a much higher percentage of the majority candidates pass the test than the minority candidates. Even though the sample size is smaller, 10 out of 14 passing is a lot less than 417 out of one or out of 562 passing. All right, I'll let you read about Fisher's exact test on your own, but that is the end of chapter 11. I truly hope that you enjoyed this chapter.